Welcome, students, to your very first day of Building Science and Mechanics. Please make sure your English subtitles are toggled on as we dive into this comprehensive explainer of your core curriculum. I am absolutely thrilled to be your guide today through the fundamental principles that quite literally shape the world we live in. Okay, let's take a quick look at today's syllabus. We're going to cover 1. An Intro to Civil Engineering, 2. The 7 major fields, 3. Modern surveying evolution, 4. Materials, specifically stone versus steel, 5. The structural load transfer path, and finally, 6. A student review and assessment. Section 1. Intro to Civil Engineering, the Grand Purpose. So, before we get into the nuts and bolts, it's absolutely crucial you understand the grand purpose of our field. Engineering is not practiced in a vacuum, It carries a profound responsibility. Civil engineering isn't just about crunching numbers for math and physics. As this quote right from your text states, infrastructure forms the very backbone of economic and social development. Whenever we design water supply systems or environmental protection works, we are ensuring the safety, durability, and sustainability of society itself. We're not just building structures, we're nation building. Section 2. The 7 major fields, specialized subfields. Now, modern civil engineering is actually made up of several incredibly diverse subdisciplines. Think of structural engineering as the skeleton of a building, like the massive, rigid steel frame of the Empire State Building. Geotechnical engineering, on the other hand, acts as the roots, kind of like the incredibly deep foundations holding up the towering Burj Khalifa. And transportation engineering? Well, that's the circulatory system, akin to the Golden Gate Bridge connecting entire communities. And here's the thing, on any real-world project, say a major highway expansion, these fields are constantly collaborating. The geotechnical engineers are out there analyzing the soil, the structural engineers are designing the bridge overpasses, and construction management is overseen by the site engineers. Those site engineers are the ones focused on the daily workflows, coordinating the manpower, managing materials, and strictly enforcing safety protocols on the ground to avoid any catastrophic risks. Section 3. Modern surveying evolution, mapping the Earth. Now, before a single brick is laid or a site engineer even steps foot onto the field, we literally have to map the Earth. It is so fascinating to see how our methods have evolved here. We've moved away from the rudimentary chain and compass methods of the 19th century right into the modern era of total stations, advanced GPS, and even drone-based mapping. Accurate surveying determines the exact relative positions of points on the Earth. In this evolution, it's a total game changer. It drastically improves the accuracy, safety, and economy of engineering works, ensuring our land boundaries and route alignments are absolutely flawless. Section 4. Materials, stone versus steel, building blocks. Once we've surveyed the land, we have to actually choose what we're going to build with. I want you to notice the transition here from traditional to modern building methods. Traditional stones, which are derived from igneous or sedimentary rocks, are excellent for static, heavy, compressive loads. Think foundations and massive bridge piers, mainly because of their incredible compressive strength. But contrast that with modern structural steel. Steel provides the ductility, elasticity, and sheer tensile strength needed to survive dynamic forces. We're talking punishing winds and massive earthquakes. Plus, as a huge bonus, steel allows for much faster construction because the pieces can be completely prefabricated off-site. Section 5. Structural load transfer path, managing gravity. So, understanding these materials naturally leads us to how they actually work together to keep a building standing upright against gravity in nature. Observe this skeletal framework. Notice how the plinth down at the base protects the superstructure from dampness and surface water. Above that, the horizontal beams and vertical columns form a really rigid grid that defines the usable space. It's like a giant 3D puzzle where every single element has a very specific job in managing weight. Now, this flowchart illustrates the absolute fundamental load transfer path. And yes, you will definitely want to memorize this for your exams. Weight flows horizontally from the slab over to the beam, which resists the bending. The beam then transfers that weight into the vertical column, which takes on the compressive load. From there, the column pushes straight down into the foundation, which safely distributes all that accumulated weight over a much larger area. Ultimately, the load dissipates right into the soil without exceeding the Earth's bearing capacity. Slab to beam to column to foundation to soil. Simple as that. Section 6. Student Review and Assessment. Critical Takeaways. All right, we have covered a ton of ground today. First up, please avoid these super common beginner errors in your upcoming coursework.
Remember, cement is merely the powdered binding ingredient, while concrete is the final composite material once it's mixed with water and aggregates. Got it? Second, pay close attention to cement chemistry. Lime provides strength, for sure, but excess lime will make your cement completely unsound. Finally, don't misjudge your aggregates. Fine aggregates, like sand, actually require more water than coarse gravel simply because they possess a much higher total surface area. For your daily study reference, I highly recommend you take a quick screenshot of this summary table right now. It cleanly aligns each major engineering branch with its core objective, from structural load resistance all the way to managing hydrology and water resources. Definitely keep this handy as you read through your textbook this week. Okay, let's test your understanding right now with a quick pop quiz based on our geotechnical chat. Which specific type of foundation system is required when the topsoil is just too weak to support a structure? Think about it for a second. Well, if you answered deep foundations such as pile or pier foundations, you are absolutely correct. Shallow foundations simply won't cut it if the surface bearing capacity is insufficient.
You guys have done excellently today. I want to leave you with this final, somewhat provocative thought directly from your syllabus. Civil engineers are responsible for transforming conceptual plans into practical realities. So my question to you is, as future civil engineers, how will you use these principles of building science to not just construct ordinary buildings, but to safely transform the grand concepts of tomorrow into the practical, enduring realities of today? Class dismissed, and I'll see you in our next explainer.